Let us now apply Kirchhoff's rules. So first let's remember what they are. There is a junction rule that says that the sum of the currents into a junction equals the sum of the currents out of a junction. And then there is the Kirchhoff's loop rule that says that the sum of the potential drops along a loop around a loop is equal to the sum of the potential rises around that same loop. So let's look at a circuit. So here we have a battery V1 in series with a resistor R1, also in series with R2 and V2, and then we have a battery V3, R3, resistor R4, battery V4. And the first thing that I want to look for is junctions. So how many junctions do we have in this circuit? A junction is defined as a location where 3 or more wires come together. So that would be a junction, and this would be another junction. Now, between these two junctions, there are 3 different paths. So the current can go around from here to there, it can go down this way, or it can go from here to there. So that means that in each one of these 3 branches, there will be a different current. So I'm going to redraw the circuit with each branch having a different color so that I can remember that through those particular elements there's a certain current flowing. So I'm going to start on the left. Whoops, I need to pick up the pen. So I'm going to have a current going through here. This is V2, and then I have R1 up here. And I get to the location of the junction. Now I'm going to draw the other branch going straight down in green, so that I remember that I have a different current flowing through this branch. And there is a third branch that goes this way. So there will be a different current in this branch. So I will have to pick directions for the currents. So I was saying earlier in an earlier video that I can tell what the direction of the current is based on whether we're starting out at a positive terminal on a battery. But in this red branch, for instance, battery 2, the current would want to go away from positive in this direction, whereas for battery 1, the current would want to go in the opposite direction. So which direction would it be? I don't know. I'm not given values for V1 and V2. And even if I were, it could be that V3 is stronger than all of them and push the current in a totally different direction that we would expect it to go in. So that is why I can pick a completely random direction for the current through each of the branches. So I'm going to pick this direction for current 1. So this is my I1. And I'm going to just completely pick a direction, let's say down in the green branch, and I'll call that current I2. And I'm going to pick the current through the blue branch going to the right. So these are just random picks of directions of currents, and I will have to stick with them. So now, remembering that we had a junction right here, we can look at the junction rule and say, well, the currents going into the junction is equal to the currents coming out of the junction. So into the junction we only have I1. Only I1 points into. I2 and I3 point out of the junction. So I can write some of the currents in, that's I1, is equal to currents out, so that would be I2 plus I3. So that is my junction rule. Now you might think, well, there's a junction down here as well. Can I use that junction? Well, of course, but let's look at it. So if the current 3 comes around this way, that means that it goes into the junction at this point. If current 2 comes down, that it means that it will go into the junction at this point. And the red current, current I1, starts from here and goes around in that direction. So that means that current I1 is going to come out of the junction. So my junction rule becomes sum of the currents in. So into the junction I have I2 and I3 is equal to sum of the currents out, which is I1. So I have I2 plus I3 equals I1, which is what I already wrote over here. So I don't get any new information from using the junction rule at the second junction. It's exactly the same as the first junction. All right, so now that I picked the currents, I am going to have to go around the different circuit elements and determine where the higher potential is. So for the batteries, I know that the higher potential is the longer terminal, so I'm going to label all my pluses and minuses based on that. But then for the resistors, let me make it a different color so it's more visible. So for the resistors, I have to go with a current. So my current 1 goes from here all the way to there. So that means that it will have, the potential will drop as the current is going from right to left in this resistor, which then means that the right side of the resistor is at a higher potential than the left side. Now we keep going with the current, and as it reaches this resistor and passes through it, the potential will drop across it. So that means that the higher terminal is on the left, the lower terminal is on the right. Then going down through this branch, I2 goes from top to bottom, so when it gets to I3, it will drop through R3, the voltage will drop through R3, so the top terminal is positive, the bottom terminal is negative. Then with I3, the current is going from right to left through R4, so then the right terminal is going to be the positive one because the voltage drops from right to left in the direction of the current. So now we have everything labeled with pluses and minuses. And the reason for that is because in Kirchhoff's loop rule, we say that the sum of the potential drops is equal to the sum of the potential rises in each of the loops. So now we have to pick loops, and I will pick the left loop and the right loop. There will be a third loop, which would be going outside the whole circuit. So this whole thing would be the outside loop. We would completely ignore the middle branch here. But we can only pick 2 of the 3 loops because the third one is redundant. So I will go around the left loop. So I'll start at this junction down here and then figure out whether any of these voltages are positive or negative, if they are drops or rises. So let me rewrite Kirchhoff's loop rule, and I'm doing the left loop, and I have sum of the potential drops, so V drop has to be equal to sum of the potential rises. Okay, so a drop is when we're going from plus to minus across an element, and a rise is when we go from a minus to plus. So starting at this point, I'm going to cross V2, and it is from plus to minus, which means that V2 is a drop. So I'll write it on the drop side. Then I keep going in this direction, passing through R2 from plus to minus, so that is another drop. And to make the resistor into a potential drop, I have to multiply it by the current that goes through it, current I1. So the voltage drop there will be R2I1. Then I continue going through here, and passing through V1, I go from negative to positive. Negative to positive is a rise, so that goes on the rise side. So I'm going to put V1 on the rise side of the equation. Then I make it to R1, and I'm going from plus to minus. So plus to minus is a drop, and that would be R1 times the current that passes through it, which is I1. Then I'm going through battery V3 from plus to minus, so that is another drop. So I have to put V3 here. And then I'm going through R3 from plus to minus, so that is also a drop, but the current that passes through R3 is I2. So I'll have plus R3 I2, and I came all the way back to the original junction. I went all around this loop, and I'm done with my loop rule. Now we'll do the same thing, loop rule for the right loop. So let's start at the same point, same junction, and go around clockwise through here. So I'm going to go up first through R3, and I'm going from negative to positive. So that would be a potential rise. So I'll put that on the rise side, and that is R3 times the current that goes through that branch, which is I2. Then the next element is the battery, and we're going from negative to positive, which is also a rise. So we put that on the rise side of the equation. Then we leave I2 and continue with I3, and I3 goes through V4 from minus to plus, which is another rise. So that is plus V4. Then around to R4, and R4, passing through R4, we have a potential drop from plus to minus, and the current that goes through R4 is I3. So we put on the left side R4 times I3, and we made it all the way back to the junction where we started. So here we have three equations for this problem. We have the junction rule, which says that I1 is I2 plus I3, and we have two loop rules. One for the left loop, V2 plus R2 I1 plus R1 I1 plus V3 plus I3 I2 equals V1, and the loop rule for the right loop, which says that R4 I3 is R3 I2 plus V3 plus V4. So given certain values for some of the quantities here, we will have enough information to solve for maybe the currents in this circuit. Maybe some of the currents that you picked here will turn out to be negative. So let's say that we're solving for current I3, and I3 is a negative quantity. Then in all of the equations where you encounter I3, so over here, I guess that's the only place, you have to enter the negative value that you obtained for I3 also in this equation, so that I1 then would be I2 minus some, I don't know, 3 amps or something like that. So if we get a negative value for I3, say, that means that I picked the wrong direction for I3 in here. So I3 should actually go into the junction, into this junction and out of that junction. So it's not a big problem. The negative sign means that we have the wrong direction, but if we were consistent with our equations, then it's not a mistake. It's just at the end of the problem you would say, well, I3 is actually in the opposite direction than I picked it.